In this video, we'll be going over the bottom-up array approach of minimum path sum. So in the 2D bottom-up approach, we can see that in each of the iteration, we are only relying on values from the current row at R, and also the row right below at R plus 1. This means we can use a single array to represent our 2D matrix. Now let's go over the thought process. So in the 2D bottom-up approach, in each of the iteration, we are only relying on values from the rows R and R plus 1. This means we can represent the 2D matrix using a single array. Then in each of the row iteration, we will be updating the values from the previous row iteration. So let's go over the pseudocode. So we're going to create an array, min sum, to keep track of the minimum sum path. And we'll iterate through the indices from grid.length minus 1 denoted as R. That means we're iterating through the rows, and then we're iterate through the columns. And if RC is at the bottom right corner, that means we're going to have one value left. So we're going to set minimum sum of the current cell to the value at the cell, grid RC, and continue next iteration. Now we're going to create a variable, current, to save the current value of minimum sum. And then we're going to set the minimum sum of the current cell to a very large number, and then we'll update it as we go rightward or downward. If R is not at the last row, that means we can still go downward. So we're going to update minimum sum if the value of going downward is smaller. So in this case, we have minimum sum R plus C. Don't forget, R plus C means we're at the current cell, but we're at the current row, but the row is just one cell downward. And since we're representing our 2D matrix as an array, this value will be the same as current, which is equal to this value. Now, if C is not in the last column, then we can update the minimum sum of going rightward if the sum of going rightward is smaller. Since R, this means it's just at the current row, and it's just to the right of it. And as we can see, we're iterating through from grid.length minus 1 to 0. That means we're iterating through from right to left. So we can just say minimum sum C plus 1. And then we'll return the minimum sum from the top left corner. Now, what's the time and space complexity? The time complexity stays the same, but the space complexity turns to O of n, where n is the number of columns. This is the min sum array. Now, let's update the code. So we're going to convert our minimum sum matrix to a minimum sum array. Then we're still going to iterate through all the rows and columns. And then if our current cell is at the top, is the bottom right corner, then we're going to have one value left. So we're going to say minimum sum of C to the grid RC. And then before we replace it with a very large number, we want to save this value because we may need it here. So we're going to save it first. So in current, it's go to min sum as C. And then we'll update min sum C to a very large value. And then if R is not equal to n minus 1, that means it's not at the last row. That means we can still go downward. We're going to update the minimum sum at the current cell if the minimum sum of going downward is smaller. So we'll set this to current. And then if C is not equal to n minus 1, that means we can go rightward. So we'll update the sum of the current cell if the sum of going rightward is smaller. Now we're going to return the minimum sum starting from the top left corner. Let me know if any questions in the comment section below.